Swayam Prabha. Digital India. Educated India.
Welcome. In the last lecture, we have been discussing the solution of Rouse model, and we have almost written the partial differential equation that we had in terms of ordinary differential equation. So, today I will take it further and talk about the physical significance of the solutions that we have written for the xp, that is the variables that appear in the ordinary differential equation. So, essentially what we have done is for the discrete to continuous for the continuous analog of the bead spring model, I am not writing the partial differential equation, but the one dimensional analog that we have been working on is something of this sort, where we have obtained the value of zetas in the last lecture. It is different for p equal to 0 and everywhere else, and then we can also get the expression for Kp using the expression I have derived. This is equal to the following. Now, you can note here that we do not write a separate equation for p equal to 0, because if I put p equal to 0 here, it is anyway 0. So, the prefactors does not really matter for p equal to 0 case. So, now you can recall that for an ideal chain, the k value was derived to be 3 kbt by b square, and therefore, for ideal chain we can write Kp as 6 kbt p square by n, and then we have also derived expression for Fp, and I am not going in details here. So, let us first look at what advantage we get from here. The one clear thing you can see from here is, if you recall the Brownian motion of a free particle, the equation we had was of the sort something like this. And now, the equation we have written, of course, this is for different values of p, looks very similar in form to what we had for the Brownian equation for the Brownian motion of a free particle. Okay. So, therefore, all the kind of math we did for the displacement, correlations, functions and so on for the free particle case will apply in this case for a particular values of p. So, in the free particle case, there is only one x, but now we have multiple values x0, x1, x2, they correspond to different values of p, but for each of those p values the mathematical form is similar to what we had for the Brownian motion of free particle. Okay. So, what essentially it means, if I start thinking at an intuitive level, is we are writing the model of a polymer chain as many equations for different p values, where each of the p values give rise to an equation that is similar to the free particle case. That is the first thing that we see here. Let us say if I am interested in the correlation functions for the displacements, now I can talk about displacements in different values of xp for different p, that is x0, x1 and so on. Let us say for example, for p equal to 0, and I am not deriving it completely, but what we can get is if I look at the correlation, this would be equal to where zeta naught is of course and zeta. Now, you can see that 2 kBt by zeta was like a diffusion coefficient in that case. Now, we have a zeta naught appearing there for a particular p value. So, for every p value we can think of a diffusion coefficient for that particular p value. Okay. I have not yet given the full physical meaning as of yet, I will go on and talk about it, but this is the first analogy you can see. In general, for p higher than 0, we can say, or also q higher than 0, we can write this as delta pq delta alpha beta kbt by kp, and I am not deriving the full expression, minus t by tau p. I only put the final result here, where tau p is given as zeta p by kp and is equal to tau 1 by p square, where tau 1 is what we get for p is equal to 1, this is for an ideal chain. That is to say, if I look at the displacement correlation functions in terms of these solutions xp that I would soon call Rouse modes, so I will refer to them as Rouse modes. These correlations decay exponentially with the time scale tau p, and that time scale basically decreases as I increase the values of p. Okay. So, the decay is faster if I go to longer values of p, larger values of p, or and decay is slower if I go to lower values of p. That is the first thing that we see. The next thing is what is more important, and that is that once we have got these values of xp, so I have transformed my r that was representing the positions along the contour to xp, I can do vice versa. So, I can start from xp and get the r, that is called the inverse transform. So, essentially if I want to get r, this would simply be x0 plus twice p equal to 1 to infinity xp cos p pi n by capital N. Okay. So, using the value of xp, I can get the values of r, and you can also note that xp basically go from 1 to infinity. That means we can have infinite Rouse modes that are present in the system. Okay. So, let us see why this is the case. So, we can prove this statement for inverse transform by using the definition of the xp that we started with, after derivation of the basis function. We had got something like this, right, and you can see like now I can plug it back in there and see what do we get. So, if I plug the value of r from there, we get so I am changing the index here to q because it is anyway a dummy index and we have a p there. So, I want to retain the cross terms. So, we had something like this. So, we get the first term becomes and the second terms this I am going to replace using the rule that we have discussed earlier, cos a plus b plus cos a minus b by 2. And so, if I integrate this, what I would get is this for the first term, and then the second term will have we have that there is an x q there, and then I will get from here basically we will pretty much get it 0 except the case when p is equal to 0, in which case what we have here is n for p equal to 0 and is equal to 0 otherwise. So, what I get here is delta P0 x 0. On the right side, what we have is sine of something of this sort. So, of course, both of these are only non-zero when P is equal to Q, and as we have done earlier, this becomes delta P0 plus 1 multiplied by n multiplied by delta PQ, that is all of this. And so, what we get is x 0, and this is sum over q equal to 1 to infinity. So, of course, since it starts from q equal to 1 and we have a delta p q inside. So, delta p 0 is not a possibility because we have taken that separately. So, what we have here is essentially gives me x p. Okay. So, this is how we have showed that the inverse transform follows the relation that we have provided here by using the definition of the transform itself. Okay. So, now we know that if I know the x p, I can get r, and if I know r, I can get x p. So, it is perfectly the kind of transformation I wanted. So, I only need to solve for x p and I can get the r values, and I can get the chain configuration if I am solving for the what I call the Rouse modes, the solutions x p. The only thing is that it is infinite such solutions that we have to solve for. Now, what I am going to demonstrate is we do not really need to solve for this infinite solutions. Each of these individual solutions also have a meaning embedded in them, and that we can see if we do certain examples, try to get some quantifiers of polymer chain and see how does that relate to the Rouse modes that we have described. So, let us say for example, I am interested in the center of mass. If I am interested in center of mass, then it is of course given by simply the integration of r over n, the whole contour, and divided by n, that gives me the center of mass. And then if I simply plug in the definition of inverse transform, we get the following. So, the first term here simply gives me x 0, because integration over n gives me capital N, it cancels out. The second term here gives me the integration which is anyway going to be 0, because we have started from p not equal to 0, we start from p equal to 1. Okay. So, what I get from here is my center of mass simply is the first or zeroth. So, the center of mass refers to the zeroth Rouse mode of the system. So, without even solving for all the Rouse modes, even if I get the zeroth Rouse mode, that already has a meaning to it. It tells me about the center of mass of the polymer chain. Okay. So, now we can think about other quantifiers and see like what do they become. So, let us say for example, I am interested in the diffusion coefficient. To get the diffusion coefficient, we want to start with the mean square displacement. So, the mean square displacement mean square displacement we can define for the entire chain. More specifically, maybe we want to define for the center of mass. If I want to define the mean square displacement of center of mass, it already captures the net diffusion of polymer chain So, let us say for example, if my polymer chain goes from here to there, I can characterize the overall diffusion by looking at the center of mass here and the center of mass here. The net motion of center of mass characterize the overall diffusion of the polymer chain. Note that I am not putting the center of mass on the polymer chain itself, because by definition the center of mass can be anywhere on the chain. It need not, it can be anywhere in the space where the polymer chain is present. It need not lie on the polymer chain or any particular segment, because of the relation that we are using to get the center of mass. It does not require that we have to place the center of mass on the polymer chain itself. Okay. So, if I am interested in this, I can define this as simply the following, where RCM is a position of center of mass, which would then be a sum over the axis x, y, z for the first modes which was this, and we already have derived what that should be, that is simply delta alpha beta 2 kBt by zeta naught t. That is what we have started with, 2 kBt by zeta naught, that is what we had there. So, using this, what I can get here is this term is simply equal to 3 multiplied, because it will be same for all x, y, z, 2 kBt by zeta naught, which is n zeta t, that is 6 kBt by n zeta t. And if I compare to the relation that we derived for 3 dimensions, the Einstein relation, in 3D, what we can get is, for a polymer chain, the net diffusion is given as simply kBt by n zeta, or we can say that d goes like 1 by n. That is, if I increase the number of segments, the diffusivity decreases. Although it is qualitatively true, it turns out that the scaling is not perfectly correct. The scaling changes with different solvents, and scaling changes also due to factors that I call hydrodynamic interactions that we discuss later, and for that we have a model called GIM model. But nonetheless, it already captures the basic feature that the diffusion coefficient will decrease if I increase the number of segments on the polymer chain, which is indeed true. The longer polymer chains have lesser diffusivity because they will diffuse more slowly in the system. So, now let us look at some other quantity that we are used to. Let us say, for example, I am interested in the end to end distance. So, the end to end distance is for our polymer chain going from n equal to 0 to n equal to capital N is simply R of capital N T minus R of 0 T, and using the definition that we started with, that R and T is equal to x0 plus twice p equal to 1 to infinity, and then we have xp cos p pi n by capital N. What we do get is x naught will cancel out, and we have something like this. This, by the way, is minus 1 to the power p. So, if you notice here, all the even terms will cancel out, because for even terms we have cos p pi minus 1 is equal to 0. Only the odd terms will remain. So, this is going to be sum over all the odd values of p xp, and actually it has to be multiplied by minus 2, which is minus 4 multiplied by sum over odd values xp. Okay, that gives me the end to end distance vector. If I am interested in the correlation, time correlation of RE, ultimately I am interested in RET multiplied by RE0, that then becomes 16 multiplied by odd values of P xpt xp0, and this we have already established will decay exponentially, and then it is going to be something like so I am not doing the full derivation here, but we already have discussed what the correlation becomes. So, now you can notice here that only the first term will be the one that will be dominant, because the exponential actually decreases as we go to progressively higher values of p. Let us say, for example, we go for p equal to 3, then we have exponential of minus 9 times what we had in the case of p equal to 1. So, exponential decay very fast for higher values of p. So, p equal to 1 is the dominant term that we will see in here. So, p equal to 1 is dominant. What this means is the first Rouse mode essentially captures the time correlation of RE. Okay. So, in summary, what we have shown so far is we have assigned two meaning to the Rouse modes. The 0th Rouse mode correspond to the center of mass of a polymer chain. 0th Rouse mode also gives us the net diffusion coefficient of a polymer chain. The first Rouse mode tells me about the time correlation of the end to end displacement, and we take the idea further and discuss on the physical significance of Rouse modes in a bit more detail in the next lecture. With that, I conclude here. Thank you.